Hello, my name is Leo. Welcome to the second part of digital logic, where we're going to talk about sequential logic. Sequential logic is logic system where outputs can also become inputs at certain time, and outputs do not only depend on the combination of given inputs, but also on their sequence, which is one of the biggest differences between combinational and sequential logic. Sequential logic circuits can be either synchronous or asynchronous. Synchronous circuits are those which change their output data all at once when clock changes its state. So clock is one of the inputs for synchronous circuits. And asynchronous circuits do not have clock as one of their inputs, and their output changes whenever inputs change. Flip-flops are circuits used in sequential logic. There are bistables, meaning they can store one of two values, 0 or 1. The common types of flip-flops are SR, Dtype, T-type and JK type. Latches is the other name for asynchronous flip-flops. Here is the main type of latches, SR, also called set-reset latch, with the two main models, NOR and NAND, which are presented here with their truth tables. Let's take this first one, NOR latch. And this first case for both S and R equal to 0. So take that R is equal to 0. Then on this first upper NOR gate we have inputs 0 and 0, output is 1, so Q is 1. This one goes down to the second NOR gate, we have 1 and 0, so output is 0. Q is 1 and Q complement is 0. And this state is called hold state, since the next output, Q next, always holds the state of the previous output Q. Then we have also reset state, which is when reset input is 1 and set is 0. Then set state when set is 1 and reset is 0. And this not allowed, also called don't care state, which is not used when both inputs are 1. Then Q is equal to Q complement, which is forbidden state, since two complements must have opposite values, so 1 0 or 0 1. And we can check it also on this NOR SR latch. Here we have also the truth table for this other NAND SR latch. Synchronous SR latch is not actually true latch since it has clock, so it is clocked synchronous, so it is also called SR flip-flop. It is also called gated SR latch since it has two gates, two logic gates in front of them. So for example, NOR SR latch has two AND gates in front of. They are level sensitive, level triggered, meaning that they copy data from input to output when clock is in high, and after that remain in the last state given from data input when clock was in high. And here we have this table. So when E, which is enable clock input, is equal to 0, its state does not change. But when clock is equal to 1, it changes, and so its state changes, and it behaves just like a simple asynchronous SR latch. Synchronous flip-flops are the true version of flip-flops. They are edge triggered, meaning that they copy input, so data input, at the moment when clocks goes from low to high, that are increasing or rising edge triggered flip-flops, or when clock goes from high to low, which is type of decreasing falling edge flip-flops. Clock input is one of the input of clocked, so synchronous flip-flops, which is often marked as arrow on their element. And here are these four types we've already mentioned as the main types of flip-flops. D-type, also called data or delay type flip-flop, is normally rising edge trigger, meaning it gets data from input, D input, as we can see in this picture, when clock goes from 0 to 1. There's also some falling edge, but they are not so frequent. And here is its truth table. So when clock has a rising edge, goes from 0 to 1, then Q next, so next output, always gets this input from D input, and it remains in the same. So D is 0, also Q next is 0, and when D is 1, also this next output Q next is equal to 1. And when there is non-rising edge on clock, then Q next always holds the state of the previous Q, so of the Q. Dtype flip-flops are the base for shift registers, we can see in this picture, and we are going to talk more about them in the third part of digital logic video. Dtype or toggle type flip-flop is defined via this equation, which is kind of XOR. It is mostly used to divide clock frequency, mostly by 2, in digital counters, so it slows clock down. We can see its truth table. So it toggles the state from output from 0 to 1 or from 1 to 0, so from Q to Q next, when toggle input, this T input is equal to 1, and when T is input is equal to 0, then it is in hold state, so the next output holds the state of the previous output, as we can see in this truth table. And finally, JK type flip-flop is a universal flip-flop which can be configured as SR flip-flop, D-type or T-type flip-flop. And it is defined via this equation. We can see it here, and its truth table. It can be, for example, defined as SR flip-flop if we put that J input is equal to set input in SR flip-flop and that K input is equal to R, so reset input. It can be also configured as D-type if we put that J input is complement of K, and to get T-type of flip-flop, we set that J input is equal to K input. Now you've learned more about sequential logic. Thanks for watching and stay with us.